Hello, my name is Caleb, and for our CBE 330 challenge problem, Laryssa, Amber, Jake, and I wanted to look at the spread of infectious diseases. Deadly diseases spreading through populations are not hypothetical situations. They are realities we have faced, most notably during the COVID-19 pandemic. This experience highlights the importance of modeling disease spread in order to predict trends and develop effective countermeasures. For our project, we wanted to go beyond understanding how diseases spread and also examine recovery and mortality rates. Additionally, we sought to explore how the size of a town influences the dynamic of disease transmission. To do this, we modeled the spread in small, medium, and large towns with varying population densities. Another important aspect of our project is exploring how diseases affect both developed and underdeveloped communities. An underdeveloped community is one that lacks access to essentials like food, clean water, and adequate healthcare. By modeling disease spreads in these different environments, we can better understand the challenges faced by various communities and devise more targeted strategies for prevention and response.
The SIRD model consists of four coupled ordinary differential equations that are solved simultaneously using the MATLAB function ODE45, which uses the RK4 method. Each of these equations represent the time rate of change of the four populations of interest: susceptible, infected, recovered, and deceased people. For initial conditions, we chose to apply the model to a population of 100,000 people, with one person being infected at the beginning of the simulation. The SIRD model we used had a modified transmission rate parameter, where transmission rate is a function of population density as opposed to a constant. The transmission rate parameter includes an additional term that is added to the base transmission rate that scales logarithmically with the population density. Added to the logarithmic term are constants K1 and K2 that aid in preventing overscaling the model with the population density. Scaling the transmission rate in this way allows for a more reasonable scaling as population density increases. Scaling it in this way also allows the population density to have a greater effect on the transmission rate for less infectious diseases, while having a lesser effect on the transmission rate for extremely infectious diseases.
Moving on to the results of our model. It highlights key findings on disease spread dynamics comparing measles and COVID in different settings. First, looking at the graphs on the left, our simulations reveal that the measles-related mortality rate is significantly higher in underdeveloped regions due to limited healthcare and resources. This is evident in the graphs, where the black line shows cumulative deaths. In developed countries, this line stays near zero, while in underdeveloped regions, it peaks at approximately 10,000 deaths, or 20% of the population. For COVID-19, moving on to the graphs on the right, we analyzed both the original and Delta strains. In small and medium-sized towns, infection spiked around day 20, whereas larger towns saw earlier spikes due to higher population density. The Delta strain consistently demonstrated higher infection rates, as shown by the red curve, which peaks higher than the original strain, showing how transmission rates affect how many people get infected. Moving on to comparing transmission rates of the two diseases. Measles has an average transmission rate of 0.6111, which resulted in about 40,000 infections across all town sizes, while COVID-19, with a lower transmission rate of 0.392, caused 20 to 30,000 infections. This can be seen physically by the red lines on our graphs, where the measles lines spike much higher than the COVID-19 lines. These results emphasize the critical role of transmission rates in disease spread. In conclusion, our model successfully captures the effects of population density, transmission rates, and recovery rates. If its flexibility allows for simulating various diseases across different conditions, making it a valuable tool for understanding and mitigating infectious disease impacts.
This project taught us a lot about gathering information on parameters and modeling real-world diseases. Originally, we simply pulled parameters from the web and put them into our code that generated all of our graphs. As you can see in the original graph on the left, everyone in the population was getting infected within the first day, which is not accurate to their actual diseases. After reevaluating, we eventually figured out we needed to divide the mortality and recovery rate by the duration of the diseases. Additionally, While we were researching transmission rate, we discovered it is extremely difficult to find the specified transmission rate for the diseases we were analyzing. It was, however, much easier to find a reproductive number for the diseases we chose. Because of this, we shifted our strategy and instead calculated the transmission rate from the reproductive number and the newly calculated recovery rate. After making these changes, our graphs look much better. The graph on the right has the specified updates and looks much more accurate with a peak at about 20 days.